Troy.
Was there anyone who actually was the owner who started the Niagara Falls power plant or had the idea of doing
Oh
it?
yeah. I mean really the main guy here was Tesla. I haven't talked about him in this class because we've just been focusing on the physicists who made the fundamental discoveries. But what you need more than, of course, the great physicists like Faraday and Maxwell, you need the guys like Edison and Tesla who figure out how to take those ideas from the physicists and actually put them to practical use. And the two greatest inventors of the late 19th century were Edison and this guy Tesla. He was born in wasn't born in the United States. He was born in Hungary, and he read articles about the United States. So he actually saw a picture when he was a kid of Niagara Falls, and read some story about how people dreamed of taking the power of those falls and putting it to useful work one of these days. And from the time he was a teenager, this was a goal of his. And he actually moved to the United States and did it. I mean, he was a remarkable guy, absolutely brilliant. And I mean, this Niagara Falls power plant, if you read on the history of technology, a lot of people consider this probably the greatest achievement in the history of technology. I mean, the first modern power plant I mean, by today's standards, it was fairly small. For instance, the power plant that is at Niagara Falls right now produces over 2 gigawatts of electricity. Okay, so that's power is energy per time. So that a watt is a unit of power. So it tells you how much electrical energy that plant is putting out per second. And so a gigawatt is a billion watts. Because that was yeah.
Well, how could it power up like LA or how?
Well, I think I'm not sure how much a modern city uses, but I know that's basically LA is powered by Hoover Dam. So I mean, yeah, a modern huge power plant like that can basically drive a whole city. And the Niagara Falls power plant, when it first went into operation, the power was being transferred 22 miles to the local, the nearest city of Buffalo, New York. And then within a few years after that, by 1900, they were transmitting the power all the way to New York City, and it was lighting up Broadway, which was over 400 miles. And then the electricity was also being transmitted down lines in the other direction to Chicago. Yes?
Now, does electricity, become weaker over distances, or could it be like 1,000 and it would be just as strong if it was like 100?
Yeah, there's no real attenuation in the. I mean, this was a problem that they had to overcome. Was if you had really long lines, of course, the more resistance you have in those lines, the more you're going to lose the energy to heat. I mean, if the lines are heating up, then you're losing that much energy. right? So but they figured out how to deal with that. The electricity we have coming out of our walls here is 120 volt electricity, okay, which is not a huge voltage. The voltage is a measure of to give you an idea, how when you buy batteries, it'll say, oh, this is a 1.5 volt battery, this is a 9 volt battery. It's a measure of the power of the battery, right? Well, it turns out for transmitting electrical power, there's a lot of advantages to transmitting it at super high voltages and with lower currents. Okay, you get less heat losses. So Tesla is the guy that really figured out, how to do that. And so a lot of engineering had gone into, figuring out how to generate this electricity and transmit it over these incredibly long distances with very low losses. Yes?
Wait, when like there's power outages, does that mean like something's wrong with the power plant, like something happened there?
Well, it doesn't necessarily have to be at the power plant that there's a problem. Right now what you have in the country is a whole bunch of power plants and distribution centers, and it's all pretty high tech. What electricity goes where, when, and like the last major power outage that was in New York, I believe something actually did go wrong at Niagara, right? But there was a distribution center, some distribution center that
There's a switch house in Canada or something.
yeah, that failed. So the source of the problem doesn't have to be right at the power plant. Okay. Now, I just wanted to tell you about a few more things. Like I said, I had the date wrong on the radio this morning. It wasn't 1906, it was 1901. But by 1901, they had figured out how to make radios powerful enough with big antennas and enough current to actually send signals a long way, and that would be picked up by other antennas and amplified and so on. And so radio became a practical means of communication over long distances. In fact, the first signal, I believe it was 1901, that the first radio signal was generated in New York City and picked up all the way in London. That's a big jump between a dozen years earlier when Hertz is in his laboratory creating signals that he can barely detect when he's standing across the room. They figured out, they started out having difficulty detecting these electromagnetic waves when they were 20 feet away, and now a dozen years later they figured out how to send them thousands of miles. Okay, let's see a few more items here. I told you that Edison invented the light bulb in 1879. Well, 30 years later, major improvement, they started making light bulbs with tungsten filaments, which Instead of the carbon filament that Edison started out with, they now use thin wires of tungsten, metal. Now, tungsten, they had to overcome engineering problems in order to use tungsten. But tungsten as a metal has a tremendous advantage in that it has the highest melting point of any metal. Its melting point is, well, in Fahrenheit degrees, up close to about 6,000 degrees. So you can heat tungsten really, really hot, and so that it's just glowing with a bright light, and it still won't melt. Most metals won't do that. So, and of course, it's a great advantage to have a metal instead of using something like carbon, because metals are very good electrical conductors. You can put more of a current through it, so you get more light. Dan?
Are the tungsten filaments the same ones that we use today?
Yeah, pretty much. So it's this, light bulbs are still made with tungsten filaments. It's the best material that you can use. What stopped Edison from using it was tungsten is actually a brittle metal, and nobody back when Edison made the first light bulbs, nobody knew how to really work with tungsten and stretch it into really thin wires. And finally, by 1909, they could do that, and so they started making light bulbs with tungsten. Yeah.
Who
That's right.
found how to do that?
Oh, who did that? I'll get it for you after class. It's in one of my books here. I don't remember. Well, this one's worth putting down too. In 1911, somebody, again, I forget the name, somebody invented electric starters for cars. The very first cars that were made, how did people start them? Nick?
And you turn this crank in the fire.
Yeah. You need to be outside the car turning a crank, and there were actually accidents that the crank would suddenly start spinning when the guy's arm was in the wrong position, and the guy that was turning his crank actually broke his arm starting his car. That sort of thing used to happen. Now, so obviously it's much better just to get in your car and turn a key. That was 1911. All right, let me just wrap up with a few major. Yeah, Nick.
If you could just start the car with your hand, didn't people steal cars? Wasn't it a lot easier to steal cars?
Oh, yeah, you'd think so, huh? Yeah, I don't know whether car theft went down when they had electric starters.
Steal a car, you had to go like that, pick it up and get in.
Yeah, no, maybe they had big alarms attached to, you had to, no, I don't know. Yes?
If they were at a stoplight, would they have to get out again and spin it?
I'm not sure they had stoplights back then. There weren't that many cars on the road, so you probably just, go when it looked safe. I don't think there were a lot of traffic rules back in the first decade of the 20th century.
But what about horses? What if they ran into a horse or something?
It's too bad for the car, probably. All right, let me just give you a couple of others. When do you think the television was?
Oh, I know.
invented?
I know. I think I know. Sometime between the 1940s and the 1950s.
That's right. It was in the 40s, actually. Right after World War II, 47. First black and white TVs came out. They didn't have great resolution. Who? Oh, there were a whole series of scientific discoveries and inventions that went into finally making up the TV. So I don't think they can really give it to any one in particular. Nick.
Did anybody, wasn't the walkie-talkie invented?
Oh, walkie-talkie? Well, they already have telephones, right?
Telephones being plugged in.
Right. Walkie-talkies, that's interesting. I'll have to look that up when that was done.
They just pretty much radios. So
But
Yeah, but with, it's a combination of telephone and radio technology, basically. So, huh?
I thought they had it in World Wars.
Yeah, that sounds right. But this isn't a complete list I'm giving you. It's just a few highlights that I picked out. So the early TVs were in 47, and then rapid improvements after that till we have what we have today. And definitely this changed the world, right? I mean, TV, you get so much of your information from TV. It brings the entertainment industry right into your home in a way that was completely impossible before. Yes?
About the radio, I heard that back then they got like this weird signal every time lightning struck. How come?
They got a weird
Like they got some
signal.
weird signal, or like when lightning struck on the radio.
Oh. Well, I don't know. I mean, if lightning strikes your radio, you get more than a weird
Not
signal.
strikes your radio. No, I mean like when lightning strikes, you can like hear this weird signal on your radio back then.
Well, the actual radio signals that we use, like, FM radio generates waves that are not too different than the kind of wavelengths that Hertz was generating in his laboratory. They're just a few meters, less than 10 feet. And obviously any source other than the music you're trying to listen to that also generates electromagnetic waves of about that wavelength is going to cause some background noise. There are sources of radio waves all around us that are not just the radio stations. So there is background noise, and maybe that is increased in lightning storms. I don't know. Okay, so there's another major invention that I can't resist putting in. And that happened the next year, 1948. The invention of the transistor.
The what?
The transistor, which is a little electrical device. I won't bother to explain it to you, but it makes computers possible, basically. So this was really the first milestone in the beginning of the modern computer age.
who invented that?
A guy named Shockley.
How do you spell it?
And then after getting better and better at miniaturizing this technology and working with it, finally in 1975, there were things called microchips, which are the basic building blocks of computers. And within a decade, of course, that gave rise to, within a few years after this, that gave rise to companies like Apple and Microsoft, and the whole computer age that we live in today, which has just transformed the world. Yes.
When were remote controls?
Excuse me?
Remote control?
Oh, remote controls. Oh, because there was a time when people wanted to switch the channel, they had to get up and walk all the way over to the TV set. It's hard to believe that people lived in such barbaric times. But the remote controls, I actually don't know. Ben.
What's the difference between like the radio waves that we're getting from music
Yeah.
and radioactivity?
Oh, big difference. It's unfortunate that the names are the same because they really don't have anything to do with each other. But at the end of this course, I think one of the last things that I'll cover is some discoveries about radioactivity. But that actually happened right around, the first discoveries about radioactivity happened in the 1890s, around the time of this Niagara power plant. But that is, radioactivity has to do with changes that take place in the nucleus of atoms. Okay, so first I have to tell you a whole long story about how people came to know atoms, and then I can tell you about that. Okay, so now there's a lot of these, yeah, Selah.
Weren't cell phones invented in the 70s?
Excuse me?
Cell phones invented in the 70s?
Cell phones. Tom, do you know anything? Okay, don't. I don't know about cell phones. They're not on my list. This isn't an exhaustive list. There's a million things I didn't put on this list. I just wanted to, like all the things you're asking about, I just wanted to give you a few highlights here. Now, there's some of these later discoveries here that obviously I haven't told you very much about the physics that went into these discoveries, and it requires a lot more than, you have to know about all the electricity and magnetism that we've studied. But in addition, you have to know a lot of other things too that I haven't yet told you, but I'm going to spend the rest of the year telling you. You have to know things about chemistry, and in particular, you have to know things about atoms. And that's where we're going next in this class, is to I want to give you, starting from the early chemistry, I want to give you all the evidence that people discovered that finally made scientists realize that matter is made of atoms, and then what the structure of atoms were. And so they finally had a theory of matter. And that, in combination with what they knew about electricity and magnetism, enabled them to come up with things like TVs and computers. Okay. So we're at a major transition point in the course now. Now there's still there's still a lot of things that I haven't told you about electricity and magnetism. For example, remember back when we were studying Franklin, and people had discovered a number of things about static electricity, but they didn't really have a theory of what was going on when they saw sparks and when they saw when objects got charged and then sometimes attracted and sometimes repelled other objects. And the first person to come up with a theory was Franklin, right? And he had this idea that there was this separate electrical fluid in matter, and there could be an excess of it or a deficiency of it, and that this explained the forces of attraction and repulsion and the movement of electricity between objects. Well, later, when people actually discovered things like the battery and how to move electricity by rotating coils and so on, it became clear that Franklin's theory really wasn't right, because Franklin had this idea of this separate electrical fluid, and the only thing that would really set it in motion was if you had an excess of it, and then it would just flow away until it reached equilibrium. But then the motion would stop. So the only time you should get movement of electricity, according to Franklin, was if you had a charged body, that had too much electricity, and the electricity, would flow out due to the pressure of this fluid. Well, obviously that theory didn't hold up in the long run, because when people actually figured out how to create continuously moving electricity, it was with objects that were uncharged. Okay, so you didn't need any excess of electricity in order to get it flowing. Now, so obviously there are major weaknesses in Franklin's theory. Now, but I never really gave you an alternative theory, did I? I mean, we learned a lot of things about electricity and magnetism, but I haven't told you very much about what electricity actually is in matter. In other words, I haven't given you a theory of matter equivalent to what Franklin was trying to come up with. And that's what I want to try to do now for the rest of the year. And if we knew, what matter was and how it was related to electricity, in other words, where the electricity was in the matter. I mean, is it a separate fluid? Is it some inherent part of ordinary matter? And if so, how is it distributed in the matter? If we had the answers to those questions, then all this knowledge that I've been telling you about electricity and magnetism would be a lot more useful. Because what do you need in order to really make use of these equations that Maxwell came up with? Well, you need to know, those equations tell you how charges give rise to electric and magnetic fields. But you need to know, first, Newton's laws of motion in order to tell you, given the fields, what are the forces and what motions those will cause. But then in addition, you need to know how the electric charge is distributed. Okay? If you don't know where the charges are, having equations that tell you how those charges are related to how they produce electromagnetic fields doesn't tell you anything. So you have to combine all this the theory that Maxwell came up with a theory of matter in order to really get anywhere in physics. And it turns out that right around Maxwell's time was when physicists figured out that matter was made of atoms and could prove it. But there was a long process of discovery that led up to that. And so I'm going to go back to earlier days and start telling you a little bit. The first evidence that matter is made of atoms came from chemistry. And I haven't told you any chemistry yet. So I want to go back and tell you about early chemistry, and then chemistry really became a science in the 18th century. That's when people figured out the basic principles of chemistry. Before that, they had bits and pieces of knowledge that I'll tell you about, but they didn't really have a full-fledged science. So for the first time, people started understanding what matter really is in the 18th century, and then in the 19th century, they proved the atomic theory. Okay, so let's start into early chemistry.
Is this a new page or just
It's a new section, that's for sure. It's worth a new page. Okay, now, what did people know about chemistry thousands of years ago? Well, one of the things they knew was they knew about some metals. You know, metals are very useful. You can work with them, you can shape them because they're malleable enough, and yet they're not at all fragile. They're very strong. So they were great for tools, knives, spears, hunting. Farming tools, so on. So there was a large amount of interest in metals. Now, how many metals do you think they knew about back then? Kyle?
Iron? No.
Yeah, they knew about iron. That's one. Ben?
They knew about brass. Oh, wait, brass is made out of iron.
Yeah, brass is copper and zinc, right? They knew about copper. Gold. Okay, let's just list them. Well, ones they knew about. Gold, silver, lead, copper, tin. Good.
They had to make that, didn't
Let me see. No, let me see. What else did they? I had a list here. Tin. Oh, and mercury. Mercury and iron. And that's it. I mean, I'm talking about, the state of knowledge back in, say, ancient Egypt. So, these were the the first 7 metals that people knew about. Troy.
Didn't like then the Greeks figure out that if you mix copper and tin, you get something in tin to get brass?
Yeah, well, bronze. Copper and tin make bronze, and yeah, so they knew about bronze. These are I just listed these as the 7 pure metals that people knew about. You can have combinations of these. Copper and tin is bronze. Silver usually appears in nature as an element of lead. So it's a lead-silver alloy that you actually find. Yeah.
What was the most common metal used?
Oh, probably, yeah, well, there was a lot of, first there was the Bronze Age, okay, where they were using a combination of copper and tin. Then after before that was the Stone Age, which, we're not, I'm skipping entirely, because it wasn't scientific enough. And then following the Bronze Age was the Iron Age, right? Now, iron is actually stronger, so that was an improvement when they went to the Iron Age. But why didn't they just start right out with iron? Troy.
Because they couldn't heat it enough to mold it.
Exactly. Iron, in order to purify iron, it turns out requires a higher temperature. They didn't know how to achieve those high temperatures, so they were stuck with bronze. When they started making furnaces and could achieve higher temperatures, then they could make their tools out of iron. Okay, let me see. Now that was around, just to give you a few dates here. Bronze Age, there was a lot of working in bronze around, say, 3000 BC. And then iron, 1000 BC. And like I say, that's because purifying the iron requires higher temperatures. And so they had gotten clever enough to have furnaces that they could get sufficiently hot so that they could actually take the iron that you find in nature, which is an iron ore, iron combined with oxygen and sometimes carbon, and if you heat it up enough, you basically burn that other stuff away and you get pure iron. Okay, now one of the other things that they were interested in these that started people thinking more about chemistry and experimenting and getting some practical knowledge was dyes for clothes. People didn't want to, if you were wearing, just animal skins and so on, you don't want to go around in dull brown all the time, right? You'd like a little more variety in your wardrobe. Well, so they found chemicals that if you soaked the clothes in them and then left the clothes to dry out in the sun, that it would turn a certain color. Now, for instance, there was a blue dye from an indigo plant. Okay, I mean, you can squeeze this plant. You get a clear liquid out of it. Then you can add to that liquid some honey and lime, and get it into mix it up, soak your clothes in it, let them dry out in the sun, and you'll have a blue shirt. Okay. Same thing, they found insects on oak trees, that if you mash up these insects, get the juice out of them, then soak your clothes in it, leave the clothes out in the sun, turn your shirt red. So, for instance, I mean, Neve is wearing a red shirt right now. Okay, that's just insect guts. Well, maybe they do it differently now, but if it had been a couple of thousand years ago, that would have been insect guts. Okay, we'll continue chemistry next week.